Hello, everyone. I'm Jesse, and this is my data mining 2025 final project. So I did my machine learning project on Clash Royale, and I named it TEAL, which stands for the Tactical Evolutionary Analysis of Ladder within Clash Royale. So just to introduce the team first, we have Jesse Retro Dong. He is the data engineer who collects and cleans all the Clash Royale battle data. And this is all accessed through the API, which I'll talk about a little bit later. We also have Jesse Access Deny Dong. He's the model lead, and so he designs and trains the ML models from the logistic regression to neural networks to decision trees and also kernels. We also have Jesse the Brains Dong, who was responsible for evaluating and visualizing the data in AUC, like or showing AUC and accuracy, and also creating plots. And then finally, we have Jesse Shadow Dong, who was a system and optimization lead. And so he was responsible for implementing the evolutionary search and deck optimization pipeline. So just to introduce the game, first of all, Clash Royale is made by Supercell, which is like, I believe, a Swedish company. And within the game, two opponents will battle off. And whenever you enter a game, you are opted 8 cards. So you can choose any 8 cards from a pool of 121 cards. There can't be any duplicates. And these are the cards that you use to fight your opponent. And so we can see on the right image, um, the cards are placed on the bottom of your screen, and you can drag cards into the playing field, which is this grid structure. That's considered the arena, and that's how you battle your opponents. And the objective of the game is to capture towers. So if you capture a tower and your opponent doesn't, then you win. So here's our mission. The mission was to find and predict the win rate of any deck, and also find the best Clash Royale deck possible. So it's a really, really ambitious task, but our team was able to successfully execute it. To start, I'm going to be talking about the data collection that occurred. So this was through the Clash Royale API, and the API is able to access players' match data, which is basically consisting of the 8 cards that one opponent used, 8 cards that the other opponent used, and then also whether or not the opponent, like who won. So if it was a win or a loss from one person's perspective. Additionally, within this API, I ran into some trouble with what data I was using. So I had first of all had to, after I like tried my initial run, I also had a filter for game modes. The reason why is because for different game modes, there's different cards that are favored. Um, and so by having all the game modes into this one data set, it would just add a lot of noise. And so I had to filter it all the way to just ranked 1v1 games. Um, Additionally, I also had to filter it to strictly include wins or losses. The reason why is because there are edge cases where two opponents completely draw, and this is when they end with the same exact tower health. So I had to filter for that. Um, and then talking about how many data points I was able to collect, the scale was with around 500 or 55,000 total battles. From these 55,000 total battles, there are 3,000 unique players, and these are going to be filtered by like the top players. So I wouldn't use like a entry level player to train my data or to train my model. Additionally, I had 121 unique cards, which is all the unique cards within the deck or within the Clash Royale as a whole. Um, and this eventually ended as a 60% win, 40% loss um, split. So the reason why it's skewed towards wins is because these are the top players, which means they're more likely to win compared to lose, right? The other uh, point that I had to cover was to find top players via clans. And so uh, the Clash Royale system is constantly changing. And the best way that I can find to find the top players was to filter for these top clans and only choose the winners. So it would be splitting them between winners and losers. So this is an example of what the CSV file looked like. On the left side, we have the player tag, which is what was acquired from like splitting each clan. And then to the right, we have the battle time. This is kind of arbitrary. Um, it wasn't really important for my model. It's just to distinguish each match. We also have the game mode, which all of them were ranked 1v1 in the new arena. And then we also have my deck and opponent's decks, which is a total of 16 cards that were used within the match. And the result is kind of cut off on the screen here, but it would just output either a win or loss for uh, the the player's POV. So now that I have all the data, I can finally train my model. And we have five different types of approaches. We had logistic regression, neural network, the kernel method, decision trees, and also the evolutionary algorithm. So um, the first one that I kind of involved with was the baseline, or to kind of set the scene, I have a baseline comparison, which is zero point 0.6, around zero point 0.6 of a true win rate. This means from all the matches that I covered within the data set, exactly 0.604 of them, or on the probability of the wins was 0.604. We also have the AUC, which is the area under the curve. This would be 50%, and it's saying that 50% of the time we have a higher score assigned to a win compared to a loss. So this makes sense because we're assuming that like there's always a win, which means it's going to be half the time it will be correct. So the first model that I used was logistic regression, or the first model approach that I used was logistic regression. Um, this was a this is basically a simple model to predict the probability of wins given the decks in the match. And so this probability is applied to all the models. Logistic regression is specifically a linear model, and it's based on a set of 242 features. So there are 121 card options for each player, which means in total there's 242 features. So 121 times 2. Um, and for logistic regression, it was able to achieve a accuracy very close to the majority baseline, where the AUC was 0.552. This is not really a good number. We want it to be closer to as close to one as possible, which means like it would have a higher probability for something that would win. Um, and so this number kind of tells us that there's a limited signal within logistic regression. So the next model that I pivoted to was neural networks, which is all the rage now. This is able to capture nonlinear interactions between cards and deck matchups. So it's not limited to just the features that I have. So we have the same input features, but there's also two hidden layers. And so there's like more analysis of it kind of going in the background. And I use Relu. Um, so I use these two hidden layers. I was getting a bad AUC, and so instead I tried three layers, but unfortunately the AUC decreased, which means that like two layers seems to be the most optimized version. Um, when using this neural network, I was able to get a better AUC compared to logistic regression, but the accuracy was still around the baseline. So it wasn't too powerful or it wasn't too accurate, um, which kind of indicates like even though this model is very flexible, it can't really overcome the noise. So just to present the data, I trained it on different data sets after like doing many different filter runs. So um, I first tried a single deck accuracy model. It got around the same. Um, and then I tried using my deck and the opponent's deck, which basically just means that it'll take into consideration the opponent's POV. And so this gave it a little bit higher, but still kind of marginal. Um, I also tried training on new players. So instead of just including all the winners, I would kind of like recursively find losers from each match. And so the new baseline for this data set would be 0.595. Um, and it was still kind of marginal. The test accuracy was 0.598, and then the test area under the curve was 0.555. So at this point, I was kind of like bashing my head against the wall. I wasn't really sure if it was even possible to train like a really strong model. So I tried different methods. I tried using the kernel method. Instead of using the original 55,000 battles, um, the full RBF support vector machine would be slow and it wouldn't really fit in the memory of my computer. And the reason why is just because it's very heavy computationally. So instead of using these 55,000 battles, I would use 15K battles as a subsample. Um, and it just makes it a lot faster. So um, from kernel methods, it's able to implicitly map decks into a high dimensional feature space. Unfortunately, even though like despite all these efforts, it still underperforms simpler models. I believe it underperformed linear regression, which means there's very little extra structure to exploit. Um, Finally, moving on, I tried the decision tree. So this was using XGBoost with a standard sklearn implementation. And from decision trees, it's used tree-based models, so it's based off gradient boosting. And the naturally for decision trees, it models the card interactions and nonlinear splits. And for decision trees, fortunately, this was able to achieve the best AUC at 0.57, which is better than the neural network. Um, and it does confirm that for deck composition or for the deck matchup, like whatever deck that people choose, it will contain a signal, but it's not enough to achieve a high accuracy by itself. So here's a total comparison. We have the accuracy and the AUC on the top, and then we compared all four models against the baseline. So we'll see here that, like we mentioned earlier, the decision tree has the highest AUC, followed by the kernel method, and then neural networks. And then finally, the logistic regression model was the worst. So here's a visualization that I made in Python. This is the ROC curve comparison. And this kind of matches what we said just earlier. For the decision tree, it has the highest, kernel methods follows, then neural networks, um, then logistic regression. And so ideally, it would have been really close to the one true positive rate, but unfortunately, we have a couple. It seems very far, so it's very close to the random 0.5 AUC. I also made another plot to kind of map out the importance of each card. So from the 121 cards, um, this is the importance assigned to each card. So we have Firecracker at the top, Tesla, Three Musketeers, and etc. Um, I don't believe this is accurate though, partially because um, the data isn't really clean, so there's going to be a lot of noise. And also, as just like a sanity check, there are tier lists of each card, and this doesn't seem to be quite matching like each tier list. Like within this list, there seems to be a couple D tiers or F tier cards. So, after developing all these models and kind of having a hard time, I eventually switched to the evolutionary algorithm. So this was to attack the second goal. The second goal being um, to find the best deck possible. And so for the evolutionary algorithm, I based this off the neural network. I tried actually with all the models, and neural networks seemed to do the best, even though decision trees had the highest AUC by itself. Um, and so within the evolutionary algorithm, I would perform 75 generations for each run. So it would start with a random eight cards out of the 121 cards, and it would kind of mutate one or two cards each time to see if it gets better or worse. And from these 75 generations, um, they tended to converge onto one deck after around 30 generations. So this was one cycle. What I described is all just one cycle of evolve deck. And then I made a second program, or I made a second script, which was multi-evolve. And so this would take 50 runs of evolve decks. This takes around uh, like 40 minutes to run. But it would take 50 runs of Evolved decks, and it would find the best deck or the score, or the deck with the best like win rate score from all of these. Interestingly enough, there was a card that kept on appearing within all these decks, which was Barbarian Barrel. Um, Barbarian Barrel is rated S tier on player tier lists within the cards. Um, but the end deck that I found from multi-deck or multi-evolve was not really similar to any current meta deck or any deck that like current people play. So here's the deck. We have the deck shown on the bottom here, but it's going to be Barbarian Barrel, which I mentioned earlier. We have the Bowler, Cannon Cart, Elixir Golem, Heal Spirit, Inferno Tower, Rascals, and the Expo. And this had the best fitness at 0.866. Um, and so I actually tried playing games with this deck against real players. Um, I played a couple games, and it seemed to be that this deck wasn't really too strong. Part of the reason was because too much um, there wasn't too much air damage, so it was just the Rascals. And then also it seems to have like a very weak push or a very weak attack potential. So although the evolutionary algorithm gave me this deck, I don't think it's that accurate. So now talking about the limitations, which is a perfect segue. Um, all the decks within the high level ranked 1v1s seem to have merits to them. So if people are playing those decks to begin with, um, or because I'm taking data from only a high skill level, um, people will already have good decks to start with. And so in this case, it didn't seem that the deck itself seemed to be like really important. It mattered more about the skill of the player itself. And in addition to this, I mentioned this briefly earlier, but there's also data limitations. So within the game, there's cards that have evolutions. This wasn't really mapped out, and so I couldn't assign like which card has which evolution. Um, there's also no tower troops, so technically there should be 125 features instead of 121 features. Um, the tower are just like the individual like attackers on each tower, and it wasn't really included within the API data. Furthermore, it was strictly a win versus a loss. Um, and the API doesn't tell me how much game tower damage occurs. If it did give me this feature, I would be able to like assign cards a higher like power, so to speak, if there was more damage on the tower. Um, and also, it doesn't really account for games that are affected by lag or AFK. So AFK meaning away from keyboard. So if someone leaves the game, they would automatically lose, or if someone has bad Wi-Fi, they would more likely or not lose. Um, and the game doesn't really account for this. So this just increases the noise within the data. Um, some more limitations. There's also a gap between how the model assumes you will play versus the actual user play style. So the issue with this is that although the evolutionary algorithm, I was able to get a final deck, it doesn't really tell you how exactly you should play the deck or how the computer thinks that you should play the deck. Some players might play more aggressively, players might play more defensively, um, or they might have different tendencies on where to put cards. So um, there's this like kind of gap between the model itself and then how a player would use this information. And like yeah, like I mentioned before, I played a couple games with evolutionary deck, and unfortunately, it felt pretty weak against other players. AKA, I lost a couple games. So finally, for my takeaways, um, it seems to be that the deck alone is a weak predictor. So even though I have these 16 cards that the opponent uses and that I use, the deck alone seems to be a bad indicator or a bad predictor, which means I need to have more features as there's too much noise within the data. And as a general statement, um, yeah, like one of the main issues that I kept trying to work with was that if the data was bad, the model couldn't perform well. And so I spent a lot of time finicking with the API, trying to find more data or trying to filter different combinations of data, but it didn't really seem to work. Um, and additionally, within the evolutionary algorithm that I created, it seems to care more about the top extremes. So even though decision trees had a better AUC, the neural networks seem to have more of these higher extremes, which seems to work well with finding like the best deck. So thank you very much. That's my presentation. I'll see you guys on Tuesday. Peace.